So what I want to present is a joint work with Thomas Galli and Markus Müller. I'm going to talk mostly about this paper. Sorry. Oh, let me just get this paper, okay? But I'm also going to mention results of the other two papers, okay? These three papers develop a formalism that exploits the representation theory of the unitary group to, for instance, classify all alternatives to the measurement postulate or the Born rule, and also it can be used to classify alternatives to the Schrödinger equation, like usually people talk about nonlinear variants of the Schrödinger equation. Okay. The main claim that I want to make here is that the measurement postulates are redundant. I will start by clarifying why I say measurement postulates in plural. And the reason is that usually in textbooks, there are three measurement postulates. The first one specifies the mathematical structure of measurements, namely that they are associated to Hermitian operators or POVM, etc. Second, the formula for assigning probabilities. And third, the post-measurement state update rule. I claim that these three statements are, these three structures are redundant. But I want to clarify, I'm not claiming that the role of measurement is unnecessary or that it is not fundamental, as in, for instance, many worlds approach to quantum mechanics. All the contrary, here we take an operational approach to the notions of measurement and outcome probability. We consider them to be primitive. But although we consider the notions of measurement and outcome probability primitive, we don't impose on them any particular mathematical structure. And is the specification of this mathematical structure that what is redundant, actually, according to our claim? Okay, so let's start by just reminding the postulates of quantum mechanics. States are raised in a complex Hilbert space. We are going to consider finite, but also infinite dimensions. Transformations or dynamics are given by the action of an element of the unitary group of the corresponding dimension. The joint Hilbert space of a bipartite system is a tensor product of Hilbert spaces. And let me summarize the measurement postulates for the time being in the following way. Outcomes are represented by Hermitian matrices in the semi-definite interval between 0 and identity, and probabilities are given by the Born rule. Okay. Okay. So is this postulate, the measurement postulate, that we are going to get rid of and substituted by any possible alternative? And to clarify what this means, let me start with just an example. Okay, so I'm going to present an example of an alternative to the measurement postulate. And in this alternative, probabilities, instead of being linear in the projector onto the pure state, they are linear in the tensor product of two copies of the projection of the projector onto the pure state. And here, the effects do not act on the Hilbert space of the system, but they act on the symmetric subspace of two copies of the Hilbert space. And the normalization condition says that all the effects of one particular measurement should add up to the symmetric projector onto two copies of the Hilbert space. Okay, it's quite similar to the Born rule, but definitely different. The first physical difference is the following. If we want to assess when two ensembles of pure states are equivalent, okay, the necessary and sufficient condition for two states to be equivalent is this mathematical constraint. Okay, this is very clear because the trace is linear. Okay, so this is the condition. And in this theory, to talk about mixed states, we don't need to use, we must not use density matrix but these objects instead. Okay. Yeah, so this illustrates that if you change the Bond rule, then you're also changing the structure of mixed states automatically. This has some exotic consequences, like for instance, if we consider a qubit, then the uniform mixture on a basis is a different mixed state than the uniform mixture of a different basis. Okay, but yeah, that's exotic, but is consistent, so no big deal. Let us see more gossip about this theory. It turns out that if we consider the Hilbert space of a qubit, this actually, because we have changed how we calculate probabilities and what is the structure of measurements, this system encodes 3 perfectly distinguishable states, a classical treat. So maybe we no longer call it a qubit. Okay, we will just say a 2-dimensional Hilbert space. Also, because of this structure, the set of mixed states of a 2-dimensional Hilbert space is not characterized by block vectors, but instead by areal parameters. Okay, no surprise here, since we are talking about higher dimensional set of mixed states. Good. Now, let us try to understand how composite systems work in this theory. So suppose that we have 2 Hilbert spaces, system A and system B, and this is a pure state, possibly entangled, pure state of this tensor product Hilbert space. And we want to calculate the joint probability of having one outcome F on A and outcome G on B. Naively, you could think that this is just a tensor product, okay, but this is an inconsistent ansatz. Because if you sum overall probabilities of all the outcomes on system A and all the outcomes on system B, you just will get the tensor product of the 2 symmetric projectors. But the tensor product of the 2 symmetric projectors is different than the global symmetric projector, which also has this term, which is the tensor product of the 2 antisymmetric projectors. And because this state has overlap in this subspace, then yeah, it would mean that the sum of probabilities that locally adapt to 1 globally do not adapt to 1. Okay, so this is an inconsistency, and also this illustrates that this theory is not locally tomographic. Okay, so this is not the correct rule for writing B local measurements, but it turns out that we can find the correct rule, and the correct rule is unique. Okay, this instead of, we call it the star product instead of to distinguish it from the tensor product, and that's how we write B local measurements on the composite system AB. And I claim that this is unique, and the uniqueness follows from 2 constraints. The constraint 1 is that the product of the 2 unit effects, the 2 local unit effects, give us the global unit effect. It's clear that here we put PA plus and PB plus. This is just unit, okay, and we get this P minus, and then we get, of course, P plus, which is the global unit effect, okay? Excellent. The second constraint is that it needs to be bilinear, this product, okay? And these 2 constraints that later I'm going to discuss in more detail uniquely specify this star product. Once we have the star product uniquely specify the formula for obtaining the reduced state for A. So suppose that Alice and Bob share this bipartite pure state. How can we calculate the reduced state for Alice? Well, is via this formula, okay? It might look weird. It's no big deal, okay? It's just perfectly consistent, and yeah, is different. And clearly this is contained in the symmetric subspace of system A. This formula has a very exotic property, which is that it violates the purification principle introduced by the Pavier group. This means that if I look at the local state space of Alice, I can write convex combinations of pure states that cannot be written as the reduced state of a larger entangled state. Okay, so in this theory, we can somehow distinguish between ignorance in our preparation and ignorance because we are discarding other systems, something that doesn't happen in quantum mechanics. So all this pretty exotic, but it's all logically consistent. So that's no big deal until now. But now I'm going to introduce another property of this theory that makes it inconsistent. And this is that the star product is not associative, okay? And this is inconsistent because it's incompatible with our notion of what is a physical system and what is a physical subsystem, okay? So the way we do physics is that these are subjective choices of the theorist, okay? I can choose to analyze a physical system on its own, or I can choose to analyze a physical system as part of a larger system, and I should get the same probabilities, okay? So this tri-local measurement could be considered by one theorist as a bipartite system according to this bipartition. And another theorist could consider it to be a bipartite system according to this bipartition. And these are subjective choices that should preserve the probability structure. But in this theory, that doesn't happen. Okay, so then for us, this theory, this alternative measurement postulate is inconsistent. But this is great because we can rule it out. Okay, maybe we can come up with the following hypothesis that all alternative measurement postulates have a non-associative star product. Okay, so let's work with this hypothesis because maybe it means that the quantum measurement postulates are the only possible ones. Okay. Good. So these are our standard quantum postulates. We are going to get rid of this one. And now we would like to find a mathematical formalism to specify an arbitrary measurement postulate. How can do this? So in the following way. This is how I denote the probability of outcome F when I prepare state psi on a single system. But how can I represent mathematically every outcome? Okay, so this probability can be seen as a function of the ray, of the state. So I'm going to represent outcome F mathematically by that probability function. And that's what I call every outcome is mathematically represented by an outcome probability function, or OPF. We could also call it effect, but effect suggests some sort of linear action in some space. And here, from the very at the first stage, we didn't want to have this connotation. Okay, so it's just a function. It can be nonlinear. It can be actually, we allow these functions to be discontinuous. It can be absolutely anything, just any function from the set of pure states to probabilities. So then the specification of a measurement postulate is that for every Hilbert space dimension, we have a set of outcome probability functions. Okay, so we have one of these sets for dimension 2, 3, 4, etc., until and including countably infinite. But we also need some extra structure because when we consider bipartite systems, if we make a bilocal measurement, okay, so I choose an outcome probability function here, and an outcome probability function here. This clearly has to be represented as an outcome probability function in the tensor product, but these sets don't tell me this structure. Okay, this is just for the time being, this is completely unstructured sets. Okay, so we need to specify this structure, and this structure is given by the star product. The star product tells me how a bilocal measurement is inserted in the effect set of the joint Hilbert space. Okay, So, and it's the functioning of the star product is the same as I have illustrated in my example. Good. Okay, so let us start by talking about some of the properties of each of these sets of outcome probability functions. Each outcome probability function, as I said, is just a function from the set of rays to probability values. I can just take a family of these functions. These don't need to belong to the same measurement, just any choice of functions. Each corresponds to a measurement. I can prepare these measurements with certain probability. So because these Fs are probability, the global probability that results from this operational procedure of choosing X with this probability and preparing the corresponding measurement is given by this formula. This is just probability theory. And because I operationally can prepare this outcome probability function, I can prepare this operationally. So then it should be one of the elements of F, big F. Okay. So then this implies that F is a convex set. In addition, I can define an action of the unitary group on the set of outcome probability functions. If you give me a function, the action of U on that function is given by transforming it to this other function. Okay, this endos this set with an action of the unitary group of the corresponding dimension. And this is great because it tells us that every alternative measurement postulate has associated some representations of the unitary group. And let's now put this in practice. Let's see that with this idea, we can constrain a lot which representations of the unitary group can be used as alternatives to the measurement postulate. Here we are going, so let's consider any dimension, any finite dimension that you choose. So this is finite in this example. And this is just a subset of the unitary group. And is the subset that preserves this ray. So if U1 is a stabilizer subgroup of this ray. Okay. Now, because of this, because we want that our representation, the alternative representation of the unitary group preserves the structure of the dynamics of pure states, it needs to happen that it must have, when we restrict the unitary group to this subgroup, there must be at least one vector that is invariant under this subgroup. And this doesn't happen for this type of representations, just triangular or triangle representations with the edges job. If you're not familiar with representation theory, that's not important. Just I'm going to say that the majority of the representations of the unitary group do not preserve the structure of the quantum dynamics. Okay, so we get rid of them. And the only ones that survive are the hexagonal representations. Okay, so this is a standard quantum representation. This is the next one, and there is an infinite series of hexagonal ones. If you're not familiar with that, I will put it in more like standard terms. Consider the following action on pure state psi. Okay, let's take the projector tensor itself n times and consider this action. This action is reducible, but it decomposes only in hexagonal representations. Okay, so then my conclusion, which is pretty neat, is that any alternative to the Bond rule must have this form. Well, here I'm making one assumption, which is that my set of outcome probability functions is finite dimensional. Analogously, the set of outcome probability functions is dual to the set of mixed states. So I'm assuming that if the Hilbert space dimension is finite, the corresponding set of mixed states is also finite dimensional. Later, I'm going to discuss this assumption more. But for the time being, let's take this assumption, and then we conclude that the most general variant of the Bond rule and of the structure of measurements that is finite dimensional, that generates a finite dimensional set of mixed states, is this one. okay, where n is a finite number. So for every n, you will have a different Bond rule if you want. Also, the way we characterize effects, it's also different because it acts on the symmetric subspace of more and more of n copies of the original Hilbert space of pure states. And yeah, additionally, you can have additional constraints on this outcome probability, on these effects if you want. Yeah, you could restrict some of them. You could make them act only in one irreducible representation of this irreducible one. So that's additional restrictions that you can put. Okay, that is perfectly fine. But in any case, we can have a coarse classification of variants of the measurement postulate for single systems that are associated to just basically about this n. This n characterize them. Good. So we have now using these two facts, we can have a much neat classification of alternatives to the measurement postulate for single systems. And now let us move to multipartite systems. So we have so let us see the properties of the star product. Okay. The first property is that I can always prepare a measurement by using an ancilla. Okay, so imagine they have my system and my ancilla. I put the ancilla in a fixed state and I make a B-local measurement and I condition on a certain outcome for the ancilla. This produces an outcome probability function given by this function of this arbitrary argument, maybe psi you can put here. And this function of psi, since I can operationally prepare it, should be an element of the set of outcome probability functions. Okay. This constraint is mathematically equivalent to this one, which maybe is more easy to understand. But for me, this is not a necessity, okay, an operational necessity. And this is, okay, this is clearly related to an operational procedure that you can do. So it should belong to our set of outcome probability functions. Our second constraint is that the convex structure of a system must be independent of the fact that so the convex structure of the set of effects has to be independent of whether I consider a system on its own or I consider a system as part of a larger system. Okay, this is a subjective choice of the theorist, so that should not change probabilities, and that's encapsulated with this formula. Analogously, the way the unitary action on my set of effects, okay, should be independent on whether I consider a system on its own or I consider a system as part of a larger system, okay? And finally, the star product should be associative, as I said, okay? So these equalities to me just relate equivalent descriptions, different descriptions of the system that are physically equivalent. They have the same representation on the physical world, but mathematically they are different, okay? But since these mathematics must to match the physical world, then hence you have these identities. Okay, so with these properties of the star product, we use them as premises for the following theorem, okay? This first theorem only deals with finite dimensional Hilbert spaces and their corresponding sets of outcome probability functions. So this theorem that we have proven reads like this. The only family of finite dimensional outcome probability function sets, F2, F3, F4, and so on for all natural numbers, equipped with a star product satisfying the previous conditions, namely this, is the quantum one. So each of the elements of each of these sets has to be represented by this formula where F is an Hermitian matrix acting on the corresponding Hilbert space of the same dimension, not copies of itself or anything like this. F is an Hermitian matrix satisfying the standard semi-definite conditions of POVM elements, and the bilocal outcome probabilities are given by the standard tensor product of POVM elements. Okay, this is the quantum thing. Okay, so first of all, we have said that our sets of outcome probability functions and star product must satisfy the previous conditions. This includes this and convexity and unitary action. Okay, and the unitary action preserves the set. Yeah, you could think that I am just substituting the standard measurement postulates by this long list of assumptions. But this is not the way I see it, because this for me is just, if you want, is what we mean. This set of constraints is what we mean when we say, when we talk about a system, a physical system, a physical subsystem, a state, a measurement, an outcome, a probability. The rules of probability that, of course, I'm giving it for granted. So these are not assumptions that are at the same level of postulating a particular structure for the measurements and a particular formula for the outcome probabilities, etc. Okay, if you want, these are the foundations of the foundations, if you want. Okay, and yeah, in general probabilistic theories, people use these all the time, implicit or explicitly, and also in categoric quantum mechanics. If they arrive at this level, depending on how much they go to less general structures, they always touch these constraints. Okay. Okay. But the second assumption that I'm making here is that, okay, so yeah, the Hilbert space dimensions are finite, but I'm also saying that the only family of finite dimensional sets of outcome probability functions. Okay, so this is indeed a physical assumption, okay, that I'm going to discuss now. We are assuming that if you have a finite dimensional Hilbert space, the corresponding set of outcome probability functions is also finite dimensional. The set of outcome probability functions is dual to the corresponding set of mixed states. So that's equivalent to state the finite dimensionality of the set of mixed states. And this is, you know, if you don't have this, you will have that, for instance, a qubit would have a set of mixed states that each mixed state is characterized by infinitely many parameters, and state estimation would be impossible. Okay, so this assumption allows to make state estimation in finite dimensional Hilbert spaces, okay, arbitrary states of finite dimensional Hilbert spaces. However, the real reason we make this assumption is because of mathematical convenience. It's because we have not been capable of dealing with infinite dimensional representations of the unitary group and their corresponding Born rules. Okay, but maybe those are also inconsistent. Okay, so perhaps this assumption can be relaxed, or perhaps it can be substituted by another assumption, namely the continuity of outcome probability functions. We have not used this assumption yet. It's just a consequence of finite dimensionality, but perhaps it's physically more justified, maybe because you know, if continuity of OPFs fails, then it means that the topological structure of your Hilbert space doesn't match the topological structure that is of this Hilbert space given by a notion of distinguishability. Okay, so you will end up in a place you don't want to be. But yes, I will state that we are making this assumption. But I would say this is the only assumption that we are making, and it is pretty justified. Okay, the second theorem is just says something completely analogous, but for countably infinite dimensional Hilbert spaces. Okay, and here we need to assume another consistency constraint, which is that if I can always use an ancilla to make a measurement, and on a bipartite system. And if I take a global measurement on this bipartite system, I'm effectively, with a fixed state for the ancilla, I'm effectively preparing a measurement for the Hilbert space A. Okay, so this, since I can prepare it operationally, each again should be an element, should be an element of the set of outcome probability functions for A. Of course, for any ancilla state and any ancilla of any dimension, and A and B of any dimension, including infinite. So with this assumption that should be part of the previous list, we arrive at the same conclusion: the standard Born rule and the standard characterization of effects by POVM elements. Okay. Okay, so the state update rule, that's another result that follows, but this is actually, this was known, it's not something that we have proven. So it basically says that if you give me the characterization of outcomes as POVM elements and the characterization of probabilities as following the Born rule, the only state update rule, post-measurement state update rule, is the standard one in quantum mechanics, is that for every outcome F, there should exist a completely positive linear map satisfying this equality, and then the rule is that, okay? So if you put more detail, like you consider projective measurements, and you consider the measurement is repeatable, you would get to the standard projection postulate, okay? But in general, that's what we have operationally, okay? Good. So that's all I wanted to say, but let me finish with my conclusions. The standard measurement postulates are the only possibility compatible with unitary quantum mechanics. If you see our work as a derivation of the Born rule, it has certain advantages compared to the many other derivations of the Born rule. The first is that we don't assume the structure of measurements, like, for instance, Gleason assumes that they are orthonormal bases, or some other derivations that they are POVMs or whatever. And it's not that we only not assume the structure of measurements, but we derive what is the structure of measurements. We don't make unconventional uses of probability, like, for instance, in the very nice derivations of the Born rule in many worlds. I would say that the use of probability in a deterministic universe is maybe compelling, but is, I would say, unconventional. Okay, it's not how we think about probability most of the time. And yeah, also we don't assume very strong properties. Like, for instance, Gleason's derivation has a non-contextuality assumption, namely that outcome probabilities depend only on the outcome, but not on the measurement this outcome belongs. Okay, we don't make these assumptions. And so now I just want to summarize everything I have said with the following sentence. The specification of the mathematical structure of measurements, outcome probabilities, and post-measurement states should not be understood as postulates, but rather as theorems. Thank you very much. I'm looking forward to your questions.
Thanks for the great talk. We have, I think, one online question already. So, Gemma, can you speak up?
Hi.
Hi.
Hi. Oh, hi. Thanks a lot for your talk. I think it's really nice work, and I think it's very important to, maybe because I'm really confused about quantum mechanics, I don't understand it. I wanted to ask about the role of idealizations in your setup. So I always feel quite uncomfortable about the fact that in physics we can only solve an ideal case, like pure states or infinite system sizes or zero temperature or particles coming from infinite and so on. And then we use this perfect solution in order to, we leverage it somehow in order to understand the real case. which is like mixed states, finite temperature, finite size effects, and so on. I find this strategy very surprising somehow. And as far as I could see from your talk, in your reformulation of quantum theory, you also focus on pure states. I would call that the first idealization. And the second one is that you kind of rely on complex numbers. That's the second idealization, I would say. And somehow I felt that this issue of these idealizations was lurking behind your discussion of finite dimensional OPFs and all of that, when you kind of have to assume that something is finite dimensional. Perhaps you could take a more constructivist approach. Probably it's more difficult, where you start, from finite dimension, from finite objects or from observable objects in some sense.
Yeah, thank you very much. So yeah, ours is a problem, is a game that deals with quantum mechanics, quantum theory, or at least some of the postulates with quantum mechanics. We keep unitary quantum mechanics. Unitary quantum mechanics is with complex numbers, so that's something that we cannot modify. Of course, all our approach with representation theory can be also applied to real. Quantum mechanics are restricted to the real. This is maybe some work that should be done. So this was part of the definition of the game, the complex. The mixed states, I wouldn't say that we have ignored mixed states. What we have done is that, so what happens is that mixed states are, basically the structure of mixed states is equivalent to the structure of measurements. If you cannot change one and leave the other. So we have all the time consider mixed states. What happens is that the structure was unspecified, or the structure was conditional on what structure you could choose to measurements, and you could do the other way around. It's mathematically equivalent to consider mixed states. So these are just dual spaces, okay? So I wouldn't say that we have ignored mixed states, is that we have left its structure open as measurements.
Yeah, I was not suggesting that you had ignored it, indeed you haven't, but just that your starting point seems to be the idealized case, namely pure states, which is the standard way to proceed, I understand. But I haven't made up my mind of how weird that is. It's certainly a little weird. And can I ask another very short question, or would you rather move to the next?
I think we have a lot of time, so you can go on.
Oh, okay, thank you. It's pretty short. When you stated your properties of the star product, have you thought about casting your work in terms of constructor theory? Do you know if that would help or not? Because some of the aspects of your work had the flavor of principles, of things that cannot happen. And I don't know, are you aware of their reformulation of quantum information theory? And could that help you?
Yeah, I don't know. I just know this work, let's say superficially, but yeah, maybe it's very interesting to use it as part of this. I don't know. I don't know is the answer.
Thanks a lot.
Thank you.
Thank you.
Maybe here in the audience, Howard.
Thanks, Luis. That was a really nice talk and results. I wanted to ask you about the associativity and how appealing it is. I found this extra condition you introduced for the infinite dimensional case very operationally natural, because you can obviously should be able to do this. And it's maybe vaguely related to a condition that Alex Wilson, I, and some other co-authors like John Barrett called regularity for a multipartite composite, that whenever you do some allowed effect on part of the composite, say with a particular state prepared, that should that should be a reasonable operation, let's say. But could we not envision a reasonable theory where you had two ways of making a tripartite, or more than two ways actually, of making probably three, a tripartite composite, just depending on which one you sort of did first? I mean, I think that relates to like, what is the operational interpretation of a symmetric monoidal category maybe? So do you have any thoughts on that that might make me even happier about associativity?
My point of view is that considering a bipartite system, so the operation of taking the star product is something that happens in my head. So I'm not doing anything in reality. I'm not even preparing any state. Okay, is saying, okay, I'm going to consider these two as a single system, and maybe I'm going to compose this with another system later. But this order is in my head. Some other theories could change the order. The situation in reality, because this product is not about which state is prepared first. It's not about time. Okay, is about what I consider my first system. Okay, so it's something that happens in my head, if you want, and should be independent of which order you take. Do you agree with me?
I think I do. Yes, I think that clarifies things a lot. So the point is, you don't have to have them both in your lab. You can find out things about an entangled state just by looking at correlations. And okay, I mean, you might say, well, maybe the correlations had to come from some interaction, and maybe the nature of this interaction specified the nature of the product. But yeah, I think that makes it much more intuitive what's going on. Thanks.
Okay, do we have more online questions? Yes, okay. So I should speak up. Hello?
Hello?
Hi, do you hear me?
Yes.
Yes. So thank you for the talk and the derivation. I was wondering, at the very beginning, you said that you take the psi states of quantum mechanics as given, as fundamental.
Mm-hmm. Yeah.
But if you want to have a realist interpretation, of course, one would like to have local hidden variables, and we know that those local variables cannot be local in Bell's sense, so they cannot obey local causality. But if they have retrocausality, so they depend on future inputs, then it's open. We don't know if that's possible or not. It's very unintuitive, but it's logically possible, and mathematically it's easy to come up with toy models of this sort. And then the role of the quantum states is clearly states of knowledge. So by definition, if you let a system evolve and do not perform any measurement, you don't gain any knowledge, you have to conserve this knowledge. And it seems to me on the intuitive level that conserving information, conserving knowledge would correspond to unitary dynamics very well. And now my question is, can you try to check that mathematically? I mean, do we have alternatives? Can we discuss states which are not just unitary with complex numbers?
Yeah. These are very interesting questions. Let's say that the scope of this work was more modest. It's just a question about the internal logical structure of quantum mechanics.
Oh yes.
So I'm not able to say or refer it to these deeper hidden variables or whatever.
Of course, but my question is, do you think this is a reasonable project for your next project, not for the one you've completed?
Yeah, it is, yes.
Okay, great.
Okay, another question in the audience, here in person. Body.
Hi, Luis.
Hi.
Thank you for your presentation. I have a question about this assumption of the finite dimensionality. suppose you drop this somehow, this assumption, and I guess you can take some psi-ontic model, for example, for qubit, like Kochen-Specker and so on, and that would like somehow, I think in your language, would be like an infinite dimensional, let's say, space. And then you will see from there that your first result, let's say that the frame functions are of this very particular type, trace f times n-fold copy of psi, is somehow not true somehow. And then I was wondering whether then when you put star product properties on the top of this, how far you can go with these psi-ontic models. Maybe there is something about contextuality or no locality related to your star product properties, or I don't know, maybe I'm just speculating. So I'm saying there could be like a reason people are happy with, let's say, qubit psi-ontic model, and that somehow is inconsistent, directly violates your finite dimension assumption.
Mm-hmm. Yeah, well, yeah, this is all very interesting. I'm not sure I understand. So even though the ontic model is infinite dimensional, that doesn't necessarily mean that at the effective level that we operate in the same, this effective level would be the level of pure states. At this level, mixed states would necessarily need to be infinite dimensional because of the ontic model underlying quantum mechanics is infinite dimensional. That's not clear to me. Okay, so so the mixed states, the dimension of the mixed states is at the same level of pure states. Okay, if pure state is an effective theory, mixed state is the same effective theory. That's compatible. Being both finite dimensional is compatible with the underlying reality being infinite dimensional. Makes sense what I'm saying?
I think we would need more time, so I think we are out of time here, but I'm
okay.
Fairly
happy
convinced,
to discuss.
Right, we can discuss somehow afterwards, but I'm fairly convinced that this qubit model goes to infinite dimensional space in your language.
Okay,
good, thanks.
Okay, very quick question out of my own curiosity. Have you tried this for real projective space or other groups on other homogeneous spaces? Do you think you recover real quantum mechanics, or would there be a problem?
No, maybe the situation is different there. Maybe there are alternatives to the real Born rule there.
Okay, so
why not?
You're not sure.
Yeah, I'm not sure. So when I started this project, you can read the titles of the first papers. The initial goal was to classify all alternatives to the Born rule, okay, to the measurement postulates. Was later on that we discovered that actually there are no alternatives.
Yes, okay. Well, we should probably stop here. So thanks, Lluis, again.
Thank you very much.